So heterogeneous equilibria. What do we mean by heterogeneous equilibria, right? Equilibria is just the plural equilibrium. So this is a reaction. In this case, we have CaCO3 decomposing to get CaO, calcium oxide, plus CO2. So calcium carbonate decomposing to get calcium oxide and CO2. And these are both solids, whereas Cr2, of course, is a gas. So let's say we have a small amount of calcium carbonate, a large amount of calcium oxide. At the same temperature, the equilibrium pressure of CO2 measured with any sort of instrument is the same in both of these two situations, independent of how much solid calcium carbonate and calcium oxide is present. If you have a pure compound, then there's no concentration. It's at the same concentration, right? Assuming that it's pure. You have pure CaCO3, the concentration remains the same, no matter how much there is, right? So it's not about how much there is, it's about how concentrated it is. The partial pressure is a measure of the concentration of the gas, right? So that is the key to heterogeneous equilibria, is that the pure phases don't occur in the equilibrium constant. So in this particular case, then the pure, way to think about this is that the pure substances are already in their standard state. Now, what's the standard state of CaCO3 solid? That's what it is. It's like CaCO3 solid. It's pure. So it's already in their standard state. So the contribution cancels out. The contributions of these don't change, and the equilibrium constant will just depend on the concentration of gas, which may not be in its standard state unless it happens to be at 1 atmosphere, in which case, if it's an equilibrium with pure substances and CO2 at 1 atmosphere, then the equilibrium constant is just going to be 1. And so that's what it really is. It's the amount, the concentration of the substance compared to its standard state. This is a little hard, the best way I've thought to think about it at this level of chemistry, once you get into chemical thermodynamics, you can dig into this a little bit more, is that really everything is referenced to their standard state, and pure calcium carbonate is in its standard state, therefore it doesn't contribute. You just get, 1 divided by 1. Okay, so that's, so everything cancels out, so you don't need to keep track of it. So the equilibrium constant in this case is simply CO2. Whether the reaction goes forward or in reverse depends only on the concentration of CO2, or equivalently, the partial pressure of CO2.